All right, and let's talk about 403. I was real happy to add this one because one thing that really irritated me is I knew the math of RSA that we just talked about, like x to the e and y to the d, and that was real easy. But whenever you see real RSA keys, they look really screwy. They look like this, begin RSA private key, and then all this junk. And I always wondered, what is that junk? How do you get the private key out of there? So I looked it up and found out it's not that hard. And so I gave a project where you get to practice creating and opening these formats. This is called ASN.1 format. And all it is like a C++ data structure. You have the version, then you have the N, E, D, P, Q. These are all the numbers we just had, and then a few other numbers like D mod P minus 1 and D mod Q minus 1, and a coefficient. So you have, these are just basically everything you need. P and Q is all you really need, but you have all these numbers, and then you just base 64 it all. So it's actually really simple, and I think there's a delimiter between them too. So that's the syntax, and you can get it with Openssl. So Openssl will generate an RSA key, and then you can parse it with Openssl GenRSA, Openssl ASN1 parse will do it. So here, you generate a key and put it in key.pem. That's what this is called, PEM format, private email format or something like that. And so there's the key. And when you open it, it will find everything in there. So it took this, Openssl, reversed the base 64 and parsed it. So now you have N, E, D, P, and Q. And these are now in hexadecimal. So this is 65,536 in hexadecimal. 1 plus 1 times 256 squared. And this is N in hexadecimal. And that's P and Q. And here's those other numbers that are related to P and Q, but not as important to us. So you can now see the public key, which is much simpler. It's nothing but the modulus and the public exponent stuck together, again in base 64, so it's a lot shorter. And that's it. And this is the form you most often see RSA keys in, this format. And it's nice to see how it works. So I had a few challenges. You get to play with these things and make nice long ones, like 2048-bit ones, ones that are long enough to actually trust these days. And then I made some challenges, which was kind of good fun. So you have find P from this key, which is a private key, and find the public key from this, which is fine. These are easy mathematics, find public from private. But then I thought you can go even further than that. I gave you redacted ones. I've removed a bunch of this and removed a bunch of that. And you have to deduce what's missing from what you can find here. And what I did, which is pretty sleazy, is I just replaced this all with A and ran it through, and then replaced it all with Z and ran it through and compared them to see what changed. That's one easy way to find out what part of it. You'll find parts of it are still intact and parts of it have been damaged. And you can take the parts that are still there and deduce the parts that are missing. And here's another one, even harder, where more of it's redacted, and you're going to have to deduce what you can and brute force through the missing bits. But anyway, and of course, in these cases, you find P or Q. Once you've found either P or Q, you've got the whole story. Anyway, so there's a few challenges. Did we just get to practice opening this up and understanding it and fixing broken ones? That's the only point of that one.